Welcome to fourth week of problem solving sessions on the course Finite Element Method and Computational Structural Dynamics. So in the last sessions we have discussed how to solve the governing differential equations by different classical method. Right? So in these sessions we will discuss how to drive the governing differential equations. So in this problem I have taken a cantilever beam of length L. Let me draw the figure. Cantilever beam of length L which is subjected to the UDL of amount Q, and it is also subjected to the point load Q, capital Q, at the middle span. Right? So for this system we have to drive the differential equations, governing differential equations. So for this I have yes, someone might is on. Santhan, your mic is on. Please turn it off. Hello. Santhan, your mic is on. Anyway, so here I have considered the deflection of a beam at any distance h as Vx, right? So we can write the potential energy of the system, that is the sum of strain energy plus the work potential. Work potential is the minus of work done on the system, right? So the for beam, the strain energy is half of EI double derivative square of derivative of deflection of beam, that is V, and integrations, that is integrated over the whole span of the beam. So this will give you the strain energy, right? And work potential, that is the work done on the system. So for from the Q load, that is UDL, uniformly distributed over the beam. So the work potential from this load is Q into the displacement integrated over the whole span. Similarly, for the work potential for the unit load, we can write by using the delta functions, and we know that delta functions, that is Hi minus Hi, that means its value will be 1 when x is equal to xi. For other x value, this will be 0. Right? So for point load also we can write the word potential in an integrations form. Right? So this is the word potential. Right? Once we have written the total potential energy, so we know that the potential energy of a system should be minimum. So the derivative of this, we will do the derivative of this potential energy, and that should be equal to 0. Right? So I have I have taken the derivative of this whole functions, right? So here we can write half is there ei, again you will difference you will take the derivative of these functions, 2 will come, that will cancel half, and then d square v terms will come, and then the derivative or the derivative of v will comes, right? This is the derivative of the strain energy, and similarly I have taken the derivative from the work potentials. So this is how the derivative will look like, and this should be equal to 0. Right? Moving to the next step, what I have done here this is the equations. Right? This I have expanded here. These terms remain the same, right? And here I have expanded the first terms. So this is this if you will see here, this one. So this will turn out to be this one, these things, right? This I have done because I want to combine all these things. Here you will, if you will see, delta v functions was there, delta v dx was there, but here delta v is not there. So I have taken the I means I have split this one, and I have integrated using UV method, and I got the delta functions here also. So once I have expanded the integrations here, so here also I got this term delta v dx, here also delta v dx, and here also delta v dx. Now I can combine all these things, and this will, in the next step, we expanded this also, this value at x is equal to 12, and then this value again at x is equal to 0, and this value minus, and minus already was there, so it will turn positive, right? So this is nothing but this is evaluated at x is equal to L and at 0. The difference of this value evaluated at x is equal to L and x is equal to 0. Similarly, this value evaluated at difference of this value evaluated at L and minus 0. Difference of that two. And then I have combined all these three terms here, right? And taken this delta v dx functions, right? And to and for these functions to be 0, all these values should be equal to all these values will be equal to 0, then only these whole functions will be equal to 0. Okay? So these terms will give you the boundary conditions of the problem, and this will give you the governing differential equations, right? So the governing differential, and if you will equate these terms equal to 0, so we can write these terms, these terms equal to 0, then only the integrations of this whole terms will be equal to 0. So this will give you the governing differential equations of the system. Right? This is how you will write the differential governing differential equations. I have skipped many steps because of the lengthy calculations, I have just given you the idea how to write the differential governing differential equations. Right? And here I have taken the part-wise integrations and expanded these terms so that I can combine these terms. Right? Any doubt in this part? Right? So in the same fashions, we can derive the differential equations of being, bar, anything, any structures subjected to load. I can define the differential governing differential equations in these patterns, in these fashions. Right? So for this, for our system which was subjected to UDL and the point load at the middle, then I can, this is L. So for this system, this is the governing differential equations, right? So if in this beam there is no point load, so you can remove this terms. If there is no Q or the uniformly distributed load, so you can equate to zero. And if your this varying load is a function of h, suppose this is ah, so you can substitute the value of Q here in the terms of h or whatever functions it is. So in these fashions you will get the governing differential equations of a beam, and in the same fashions you can derive the differential governing differential equations of a bar also, right? Where Q is the distributed traction force and Q is the point load here, right? Any doubt in this part? So in this problem, first I have taken the potential energy functions and then taken the derivative because for any system to be in a stable equilibrium that should be minimum, so that the derivative of the potential energy function should be minimum, and from that I have split the terms so that this will be uniform and this will be extra terms, and this will give you the boundary conditions for a system, and this will give you the governing differential equations, right? Any doubt in this part? So I'm moving into the next part. In this, we have to determine the boundary conditions of the wave problem. So in this equations only we have seen these four terms will give you the boundary conditions, and we know that for this whole expressions to be zero, each and equal term should be equal to zero. So this term should be also equal to zero. This term should also equal to zero. This one also should be equal to zero. This one also should be equal to zero. Right? So here So here either this term will be 0 or this whole term will be 0. Here also either this term will be 0 or this whole term will be 0. Either these terms will be 0 or this whole term will be 0. So that is what I have written in the second problem. Right? Which was the expression. So all these terms should be equal to 0. Right? So from the first terms you can see when at h is equal to L, either these terms will be 0 or these expressions will be equal to 0. Similarly, here is also x is equal to L. So it will see either this value will be equal to 0 or this value is equal to 0. Right? This value gives you the moment, value gives you the shear force. Right? So at x is equal to 0 also I have written in the same process. Right? Either this should be equal to 0 or this one, and this one is also at the x is equal to 0. So either this should be equal to 0 or this one should be equal to 0. Right? And in this in our problem we know that during the derivations, I have taken the origin at this point, so this x was varying from this point like that. So here if you see at x is equal to 0, this will be your x is equal to 0 and this will be x is equal to L, right? So here we know that at x is equal to 0, this deflection, that is v, will be equal to 0 and the slope will also is 0 because this is a friction. So dv by dx should also be equal to 0 at x is equal to 0, right? So at x is equal to 0, this would be equal to 0 and this would be equal to be 0. But at x is equal to L, we know this quantity won't be equal to 0, so this term should be equal to 0, right? So that is what I have written in the second slide. At x is equal to 0, this should be equal to 0, and this quantity is equal to 0. And x is equal to L, this term should be equal to 0 because this should not be equal, this can't be 0 at x is equal to L, so this term should be equal to 0, must be equal to 0. Similarly, this should be also be 0. And in the previous sessions, we have seen how to identify the boundary conditions, whether it is essential or the natural one. Right? So that we identify from the governing differential equations. Right? So here you will see the governing differential equations is these things, and here the order of the derivative is 4. Right? 2 here, 2 here, both will be combined here. So the order of governing differential equations is 4. So according to the method we have discussed in the previous sessions, 2p will be equal to 4. So p will be equal to 2 here, right? And essential boundary conditions will be the one whose value varies from 1 to 2p 0 to 2p. So this was so here p value was 2. So essential boundary conditions vary from 0 to p minus 1. So that is 0, p here is 2, so p 2 minus 1 is 1. So the here for 0 it will be v, and for the one order derivative we can write dv by dx. So all the boundary conditions with value of v or dv by dx, that will be your essential boundary conditions, right? Similarly, we can find the natural boundary conditions. Once we have the differential governing differential equations and we know the order of differential equations, from that we can equate 2p equal to order of differential equations, and from that we can find p, and once we find the p, we have the conditions how to find the essential boundary conditions and the natural boundary conditions. So any doubt in this part? So till now we have discussed how to drive the governing differential equations of a system and how to classify the boundary conditions, and then after defining the boundary conditions, how to identify which boundary conditions is which one, right? Whether it is Dirichlet boundary conditions or Newman boundary conditions. So that is nothing but essential boundary conditions or the natural boundary conditions. Right? So this is the simplest method that we have discussed in the previous sessions also. Once we know the order of differential equations, we can easily identify which type of boundary conditions is essential boundary conditions or natural, and which one is natural boundary conditions. Any doubt in this part? Moving to the next problem. Here we have to try the weak formulations, right? Weak formulations from the of the above problem. For the weak formulations, first we have to find the strong formulations that we find from the governing differential equations, right? So for the above problem, this was the governing differential equations, right? That we have derived in the first process. So this is the governing differential equations, and here we have considered the trial functions as v bar x, right? Or v cap x, and then we can find out the domain residue, right? After substituting the trial functions in the governing differential equations. So here I have substituted the trial function, that is v cap x, in the governing differential equations. So this will give me the residue. And according to the weighted residue method, we can write these equations. So this is nothing but the strong form of weighted residue method. With the strong formulations of weighted residual method, and from this we find out the weak formulations, right? So here I have split the terms. So this is the first term, that is this one, and then I have taken this term as the second term, and this one as the third term, right? And once we will do the integrations by part of these terms and expand this one, right? So that the here, if you will see in the different Jordan differential equations, the order was 4, right? So if you choose the trial functions, here you will have to take the trial functions that should be also of order 4, right? So in the weak formulations, what we do, we shift the order of means order of the trial functions from these trial functions to the weight functions, right? So here we have to satisfy that this trial functions should be of order 4, but here only w is there, right? So there is here we can take any order of weight functions. So from the in the weight formulations, what we do, we shift the order of requirement of order in the trial functions to the weight functions, right? So that we can do by expanding these terms using the integrations by part. That's why I have taken these terms only, because here there is no derivative of there is no b cap functions here. So I have kept these terms as it is, and I have expanded these terms in the next series. So I have done the integrations by part. So I have taken this as the first term and this one as the second term. Right. So this is how it will expand. And then again I have done the integrations by part of these functions. So this is how it will expand. Right. So if you see earlier, the order was 4 for these b cap functions or the trial functions. Now if you see here, it has been shifted to the weighting functions or the weight functions, and now the order on the trial functions is 2 only, and here on the weight functions is also 2. So from 4 it has 2 has been shifted to the weight functions. So I have substituted the value of this in the weighted residual form. This is what you will get, and this is nothing but the weak formulations of the governing differential equations. This in this I have rearranged the terms and I have taken the terms which has V bar B bar terms, right? And rest all the terms I have taken on the left hand side, right? I have rearranged these terms, and this will give you the later on you will see this these terms gives you the, or we can write these terms like this. In a general fashion, we can write like this kx is equal to f. So these terms will give you the stiffness matrix, right? So this is how we write the weak formulations, right? If the governing differential equations is given to you, so from that we can find out the weak formulations by using the weighted residual method, right? Once we write the a strong form, and from a strong form we will do the integrations by part to reduce the order of trial functions, right? And then we will get this weak formulations. Any doubt in this part? So till now we have discussed how to write the governing differential equations, and then identifying of the boundary conditions, and then generating the weak formulations, right? So in the next problem I will show you how to write the stiffness matrix, right? This problem, it is asked to obtain the stiffness matrix from the weak formulations of weighted residual method. And in this problem I have taken the bar, right, axial bar of length L, which is subjected to the traction force of amount Q, right, which is the material property, right, V is the area of cross section and L is the well modulus. Right. So for this we know that the Jordan differential equations is these terms, and you will when you derive the weak formulations, so it will look like this. This is the weak formulations of the Jordan differential equations, that is this thing, and this denotes the governing differential equations of this problem, that is a bar subjected to q amount of traction force of length L, right? So from these terms we have to find the stiffness matrix, right? So here I have taken the, here if you see the order of trial functions is only one, so here also I have taken the trial functions order of 1, that is a0 plus a1x, and here I have taken the boundary conditions, that is at this point, that is I have taken this as the origin, so at this point x is equal to 0, the deformations will be u1, and at this point, that is x is equal to a, the deformations will be u2, right? So once you will substitute these boundary conditions in the trial functions, that is at x is equal to 0, that v v cap will be u1, and at x is equal to a, v cap will be u2. So once you substitute that these boundary conditions in the trial functions, you will get the value of a0 and a1, right? And after substituting the value of a0 and a1, this is how the trial functions will look like. That is 1 minus xyl into u1 plus xyl into u2, right? done nothing. I have just substituted the boundary conditions for the that is at x is equal to 0, that will be u1, and at x is equal to l, this will be u2. So this is how we can write the trial functions. But in the weak formulations, if we see this derivative of this trial functions is required, so I have taken the derivative also. And here if you see in these trial functions, this should be equal to, this is equal to weight, right? We can call it w, this also we can call it w2, right? And this is also this we can define as a safe function also, right? So we can write n1, and this one also we can write n2. So in the generic form we can write the trial functions in this n1, n1, n2, n2, right? And in this case n1 will be 1 when at x is equal to 0, and n1 will be equal to 0 at x is equal to n. Similarly, for n2, at x is equal to 0, n2 will be 0, and at x is equal to n, n2 will be 1. That is the definitions of the safe functions, right? So I have taken the trial functions according to the weak formulations, and in the weak formulations, the order of the trial functions was 1, so I have taken the one order term only here, and substituting the boundary conditions, I got this one, right? So I have written here, again, w is equal to nothing but the safe functions. So w1 is equal to n1, that is 1 minus x y l, w2 is equal to n2, that is x y l, right? And here in the weak formulations, if we see the derivative of dv cap by dx is required, and dw by dx is also required. So here I will take the derivative. So dv by dx is nothing but 1 minus l. Here the derivative is minus 1 by l, and here it will be 1 by l. In the same way, I have taken the derivative of first two unit functions and second weight functions, w1 and w2. So this is the value of dv cap dx. This is the value of d1 dx and d2 dw dx. This is the generic form, and we know that according to the weighted residual method, the summation of w1 ra should be equal to 0. Right? So this will go, and then in the next slide I have just substituted the value of these terms. Right? Here if you see, I have written the generic form of this formulations of weighted residual method, and then I have substituted the value of dv cap dx, that is the derivative of trial functions, and then derivative of weight functions in the first term, and here the weight functions in all the terms. Right? For I equal to 1, so this will be dw1 by dx. Here this will be d1, and here also not d1, this will be w1, this will be w1. So here I have substituted dw1 by dx, that is minus 1 by l. A will be remain same, and dv cap by dx, I have substituted the value, that is minus 1 by l into u1 plus 1 by l into u2. Then in these terms, I have substituted the value of w1, that is 1 minus x by l, and we know that these terms, that is a into dv by dx. dv by dx is nothing but the strain. So this quantity gives you the point load. So this is what I have written q, and then again integrations 0 to L, and W1 I have substituted, and Q is the tractions, right? Surface tractions applied to the bar. And integrating these terms, here this is constant, no value is dependent on the x. So here we integrate this term and we can write A by N here minus U2, and here if you see, if you substitute here L once, so this will be 0. So, here minus will come here, minus I will come here. So once you substitute the 0, so 1 minus L by L, that is 1. So 1 minus 1 will be 0. Then we will substitute 0 minus of this. So 0, once you will substitute the 0, so these terms will be 0, that, and remaining will be 1 here and Q there. So that is what I have written Q at x is equal to 0, but here minus terms will also comes. And once you will integrate these terms, so this will be Q L by 2. Okay. Similarly, I have done for I is equal to 2. I vary from 1 to 2 because here we have in the weight functions you can see we have two terms only, W1 and W2. So for I2, we will substitute the value of dw2 by dx, and this value also we will substitute, and these all the terms. So this will be these things, right? And integrating the terms when we substitute I is equal to 2, this will lead to this term. So from equations 1 and equations 2, we can write the combine. We can combine this one equations 1 and 2, and we can write like this. That is AEL, and here I have separated this U1, U2 from the first equations and U1, U2 from the second equation. So we can write in the terms of matrix form like this. Here the minus times here. So this is the nothing but the stiffness matrix. Right? So this is how we drive the stiffness matrix from the weak formations. So in this sessions we have seen how to drive the governing differential equations, and then how to identify the boundary conditions, and then how to generate the weak formulations, and from the weak formulations how to drive the stiffness matrix. Right? Any doubt in this part? So here I have taken the bar for the easiness of the calculations. In the same fashion, you can put the stiffness matrix for this beam problem also. Here, these terms, once you will substitute the trial functions in this in this way, and you will evaluate in the same fashions we have done for the bar. This will give you the stiffness matrix. Right? Any doubt in this part? If you have any questions, any query, you can ask. So in these sessions, we have seen how to drive the governing differential equations. So in these sessions, we have seen how to drive the differential equations of a system, And then from the differential equations, once we have derived the differential equations, how to identify the boundary conditions, and from the boundary conditions, how to identify which one is natural boundary conditions and which one is essential boundary conditions. Then we have seen how to generate the weak formulations of the weighted residual method, and then from the weak formulations, then from the weak formulations we have generated the stiffness matrix of the system, right? So you can try here. I have generated the stiffness matrix of the bar. So in the same fashion, you can uh, drive the stiffness matrix for the beam. Right? If you have any doubt, you can ask. Otherwise, I will close this session. Okay, because I think so everyone has left. So I am closing the sessions.
Yeah, sure, that's
Oh,
fine.
okay.